Okay, so to begin with, one thing that you usually look at in a trig class is you look at what the graph of an inverse sine is. I'm going to start with the inverse sine and kind of look at it that way. And there's a couple of things. This is what the graph of an inverse sine looks like. Now, one thing I want to just kind of show you on this is if you had the graph of a sine, which everybody usually remembers what the graph of a sine looks like, you would kind of have a situation looking like this. You don't have to draw this graph out, but I want to just kind of use this to show you why the graph of the inverse is the way it is. So if you have a sine, you learn that it cycles through these 5 key points like this. And then when we do an inverse, you know, what you're really doing with an inverse is you're really flipping it. You're rotating it and then flipping it. So what happens on this is what we do is we end up taking off this little piece right here and that little piece right there so that we have a one-to-one function. Do you guys remember what a one-to-one function is? It passes a test. Do you remember what that test is? It's called the horizontal line test, okay? So a one-to-one function has got to be something where every horizontal line passes through one. Not to be confused with the vertical line test, one-to-one function. And you can only do an inverse of a one-to-one function because if you didn't, then you would have a then you would have a graph that looks like that, kind of like a snake, and that wouldn't be a function, right? So one-to-one functions, what we do in the inverse sine is we chop it off and we define it from negative pi over 2 to pi over 2. So that's a real important thing that you generally learn in a trig class is the range of the inverse sine. And you want to write this down because this is important, is negative pi over 2 to pi over 2. And the domain is negative 1 to 1. Okay, and the way that I remember that is, well, okay, it's real simple. What is the range of the sine? The range of the sine, what's that? Negative 1 to 1. Okay, and when you do an inverse, the range becomes the domain and the domain becomes the range. So notice that the negative 1 and 1 on the sine graph now go to the x-axis. And then like the negative pi over 2 and pi over 2 go to the y-axis because we flip things. That's what we do. So that would be what the graph of the arc sine or the inverse sine, they both mean the same thing, looks like. Does that look like something you did a little bit in trig? Okay. No, usually don't go with that too much in depth, but at least get the idea of what the way the graph works. Okay, so what we're going to do is the next thing that I do want you to do, and I'm going to erase this, is I want you to, at the side, just draw put like an x and y axis there. Because what we're going to try to do is draw the graph of the derivative. That's a good way to begin this. So just draw yourself like an x and y axis. Okay, and then let's try to graph, since the goal on this is you know, what's the derivative of the arc sine of x. Okay, so let's just kind of put a negative 1 there and put a 1 there and so forth like that. And let's just kind of think about what this derivative is going to look like. Okay, so if we start here, what kind of derivative do you have there? My pen is the tangent line. What does that look like? Like super big, right? Very big. That's very steep, right? So it's going to start way up there. Okay, how about what's happening to my slope? Is it getting bigger or smaller? Smaller. It's getting smaller. So that means that derivative is going to go down. Okay, right around here, maybe if I did a better job of drawing this, that's a 45-degree angle. So what did we say slope of that was? 1. Okay, so probably when we get to 0, we're going to have a y value of about 1. Then what happens is the derivative is still positive, but is it getting steeper or smaller? Is the derivative getting bigger or smaller? Bigger. Bigger, right. Okay. So see what happens to the derivative. It starts big, it gets smaller, hits 1, okay, then it starts getting bigger again. So does that make sense that it would do something like that? Okay. So we're going to go ahead and just kind of sketch that out like this. So the idea is going to be that when you do your derivative, you're going to start real big. You're going to get right there, the slope is about 1, and then you're going to end up real big. So this graph does something kind of like this. And it's only defined from negative 1 to 1, so it looks something like that. Okay, it looks like a parabola. It's not. but it kind of resembles one. Okay, so what I'm going to look at is we're going to look at what the derivative is, and I'm going to show you how to derive the derivative on this. This one ends up using some implicit differentiation, I believe. So the first thing is, if you're going to find the derivative of the inverse sine, you have to understand what this means. Okay, and here's the idea. If you have just like this, if you just have y is equal to sine x, let's write that down because I want to remind you of what this is in trigonometry. If you're doing an inverse, okay, like in college algebra, what did you learn to do? You switch the variables, right? So we're going to change that y to x, and we're going to change that to y like that. That's how you do an inverse. And then you got to solve that for y. If you solve that equation for y, the simplest way to do that is to just do the inverse of both sides. Like that, and then that'll kind of give us what we're after here. So what we'd end up having is we would have, when we do the inverse of the sine, that gives y, then we'd have y is equal to inverse sine like that. So what we end up having is, I'm changing this thing to this thing. See, this thing means the same thing. So we're gonna work with doing the derivative of x equals sine of y, okay? Now, the other way that might help you to understand this is this. Okay, when you're doing an inverse sine, and like if you do an inverse sine, let's just say you were doing the inverse sine of something like square root of 2 over 2 to keep it simple, okay? What that means is the answer to an inverse sine is an angle, right? Okay, this is more like a point on the unit circle. I'm keeping it simple for you. What angle has a sine that's the square root of 2 over 2? 45 degrees, right? Okay, so what that is that angle is pi over 4, or 45, and then that point on the unit circle is this. That's what you're doing with an inverse, is you are finding an angle, okay? So what we're going to do is, we're writing this really like this. We're going to change the y equals inverse sine to x equals sine y. They mean the same thing, exactly the same thing. Okay, so when we do this, what we're going to do is we're going to differentiate this thing, and watch this carefully and write this down. So we're going to differentiate that implicitly and see what pops out of this then. Okay, so hopefully if we do this correctly, we'll end up with a formula for the derivative of the inverse sine, okay? Okay, so when we do this, it's going to go like this, okay? First of all, the derivative of x is what? 1, that's easy enough, okay? Now, what would be the derivative of the sine y? Now, remember, we're doing this implicitly. What would you have? Cosine y, then what? dy over dx, good, okay? You're doing this implicitly. The variables don't match. So we know the derivative of the sine is the cosine, but the variables don't match, so we have dy over dx. And what we have to do is we have to solve this equation for dy over dx. So the way to do that is to divide both sides by the cosine of y. Okay, like that. Okay, so that's going to cross out. Now we're going to have dy over dx equals 1 over cosine y. And remember, what our goal is on this is to figure out the rule for the derivative of the inverse sine. So we still got a ways to go on this. So over here I'm going to write dy over dx equals 1 over cosine y. Okay? And then this is kind of a thing when mathematicians are doing stuff like that, they oftentimes going to just pull out, just kind of apply a trick. So the trick we're going to do is we're going to do dy over dx equals 1 over the square root of the cosine of y squared. Right? You agree that that's the same? Yeah, the square root of something squared is itself, right? The reason I do that is because of an identity. I've got a trig identity that will be very, very useful on this thing. So we know that we have the identity sine squared y plus cosine squared y is 1, right? Okay, that's the fundamental one. So what I'm going to do is I'm going to move that to this side so that I get cosine squared y equals 1 minus sine squared y. So I'm going to change this thing right here to that. Okay, like that, just using a fundamental identity. Okay, so now what I'm going to have is I'm going to have dy over dx is equal to 1 over the square root. Now replace that with 1 minus sine squared y like that. Okay, so we're actually fairly close to having this done now. There's one other thing that we have to do on the problem. Okay, and you have to look at this kind of carefully. We actually know what this is. So if you look at this thing right there, x equals sine of y. If I square both sides, I get what that's equal to. That's equal to x squared. Okay, so what I do at the end of that is I replace that with x squared. Okay, and then that's what the derivative is. So your derivative formula for an inverse sine is going to be 1 over the square root of 1 minus x squared. That's it. That's where it comes from. Did you guys follow that any? Or at least sort of? Okay. Derivations sometimes are a little hard to follow. The key thing on this one is it was implicit differentiation that we've learned how to do. And then I changed the cosine to cosine squared y under a square root. Then I use that identity. And then the key thing is sine y is x. So therefore sine squared y is x squared. Okay? So what you need to get from this is that's the rule for when you do a derivative of an inverse sine. That's where that comes from. Okay, does that make some sense? Okay? All right, you don't have to be able to do the derivation, but man, it's nice to know where this stuff comes from. Okay? So here's what you want to have down is the general rule for the derivative of the inverse sine is 1 over 1 minus x squared, and then that's on negative 1 to 1, but it excludes negative 1 to 1, and I'll explain why that is with a graph. If you look at this, it's kind of hard to tell on this graph, but what happens is when you get to that point right there, doesn't that tangent line look like it's vertical? It actually is. It ends up being vertical, and if you have a slope of a tangent line that's vertical, it's undefined, isn't it? So what you end up having is the derivative of an inverse sine does not apply to negative 1 and 1. It only applies to what's in between. Does that make any sense? Okay. Now let me show you one thing on the graphing calculator. Why don't you get your graphing calculator out and put this in. And I want to show you this also. So what I want to have you do is actually two things. Or let's just do this one thing. I think this will be fine. Let's put in the derivative that we got, the formula. Let's just put in 1 divided by, and then do the square root of 1 minus x squared. Okay, like that. And let's graph that from negative 1 to 1. Okay, so we're going to graph this, and then we'll kind of see visually if that's what we expected the derivative to look like anyway. We kind of determined that it kind of looked like a parabola. So let's do, for the window, let's go negative 1 to 1. Okay, like that. And for the y's, let's do something like, we can start at 0, and then we can go up to like, 20 or something like that. So no, let's actually just go 10. Let's just go 0 to 10 by a scale of 1 like that. Okay, so let's try that viewing window. Graph it out and see if you don't get that kind of U shape. Now, like we had. Let's see what we got here. Okay. Okay, so you're going to find that everything we thought was there in the graph of the derivative is there. Notice that you had the derivative is 1. That's where you had kind of the 45-degree angle. If you look at that, you see how the derivative just goes almost to like an asymptote. Actually, you do have an asymptote right there. So if you have 1 over square root of 1 minus x squared, what would happen if x was equal to 1? Wouldn't that be undefined? Yep. How about if x was negative 1? Would that still be undefined? Yes. Okay, so that's what's happening on that graph is you end up getting this. Okay, so you actually have asymptotes there, so hopefully that'll help you to understand why the derivative is not defined at negative 1 and 1. Okay, like that. Okay, so that's what you want to get out of that is that's the rule for an inverse sine, and it's only on that particular domain for x values negative 1 to 1. Okay, does that make sense? Your job is to memorize that rule at a minimum. It's nice if you follow the derivation. Okay, so what I want to do with the next page, we're going to do some derivatives. Now, what I did on this one is I gave you kind of a picture of this graph. So this one right here, this is the inverse sine. That's the graph that's in black. Okay, this is the graph of 1 over the square root of 1 minus x squared, like that. So that kind of gives you the information that we need to see on that. Okay, we're going to go ahead and do some derivatives. And again, you're following the rule. You got a brand new rule that you have to memorize. And by the way, if you take Calc 2 in a future semester, these things show up quite a bit. Particularly inverse tangent shows up a lot, as does inverse sine. So you got to remember it, maybe even be able to figure it out if you have to. That's one of the benefits of learning how to derive stuff. Okay, so let's do this derivative. Now, what we're doing is we're following a chain rule on this. So really what we have is we have a function right there. So we're just going to follow the derivative, do exactly what the rule tells you to do. So the rule says if you have the derivative of an inverse sine, it's 1 over the square root of 1 minus x squared. But don't put x squared there, put this there, because that's a function. So you're going to put that there like that, and that's half of it. Then what do you got to do? It's the same thing over and over again. What's next? Derivative of what's inside by chain rule, right? So you got that chain rule going on. So now you do derivative of 3x. And then you simplify it, and then you're done. So that's how you do that. You always just do 1 over the square root of 1 minus the function squared times derivative of function. So that's going to give derivative of 3x, of course, is 3. So that will give 3 over the square root of 1 minus, and if you square out 3x, you get 9x squared. Okay, so that would be the derivative. That's as simple as you're going to take that. You don't have to factor. You could factor 1 minus x squared, but you don't have to, because it would just be 1 plus 3x, 1 minus 3x, like that. So that's a standard, straightforward example. Okay, does that make sense?
I kind of plugged in a 3 on the bottom. I kind of figured it to a 9.
Okay, why did I put it into there? Okay, see, the rule says that whatever's there goes there. Okay, and you have a chain rule for this also. So since that was a 3x, we said 1 minus 3x squared. And that whole thing becomes squared. So think of it as whatever this argument is goes there. See, that's why I did that. I did 1 minus 3x squared, not 1 minus x squared. You see what I mean? Like if that was the sine, the inverse sine of a logarithm of something, well, then you would have 1 minus the logarithm squared. You see what I mean? Okay, so it plugs in like that. Okay, everybody with me on that then? Okay, that's pretty straightforward if you know the rule. Now this one, again, is a chain rule. So it goes like this. The big function is the inverse sine of something. So when you do the derivative, it's going to go like this. You say 1 over the square root of 1 minus, and then what do you put in to square? ln of x. That's what you were asking. Okay, so that thing goes right there. Okay, you got that down okay now? Okay, very good. Okay, then what else you got to do? Derivative of ln x. That's your chain rule, like that. Okay, it's all set up, ready to go. Now, really all you would do with this one probably is you would have 1 over the square root. You can write this as ln squared x, just like you do sine squared x is the most common way to write that. And then the derivative of ln x, what's that? 1 over x, okay? And then really all you'd want to do on this probably is just write this in one fraction. I would just put the x in front of the square root, and then write the answer like that. So that would be what the value of that derivative is that, okay? All right, does that look good to everybody? Those two right there are very straightforward chain rules for an inverse sine, okay? Now what we're going to do now is we're going to kind of mix these up a little bit here and do some other rules that go along with this. So again, it's all about the chain rule. So when you look at example 3, what's the big function? What's the biggest function there? Cosine of something, okay? All right, so how do you do a derivative of a cosine? It's negative sine of something times the derivative of something, right? Okay, so you got to apply it that way. You always got to look at the big function. That says f of w. I think that was intended to be f of x. Okay, those things got to match. Okay, so we're going to have f prime of x goes like this. So we're doing the cosine of something. So that's going to be negative sine of that something, which is an inverse sine of 2x. Then you got to multiply by the derivative of what's inside, which is an inverse sine of 2x. So that's how you set it up with the chain rule, okay? All right, now what you're going to do with this one is there's not really anything you're going to do with this. This is just going to come down, and you're going to keep writing that as negative sine of the inverse sine of 2x. Not going to be able to do anything with that, okay? Then you're going to apply the rule here for the inverse sine. Okay, so when you do the derivative of the inverse sine, like we've been doing, what is it? It's 1 over the square root of 1 minus something squared. What goes in the parenthesis? 2x. There you go. Okay, like that. Okay, that's half of it. Then you've got another chain rule, and this is where students a lot of times don't pay attention. You also got to do the derivative of 2x. So you have a chain rule inside a chain rule, right? Okay, everybody follow that okay? All right, now we just got to clean it up and see what we got here. So we have negative sine of the inverse sine of 2x, like that. Okay, that's going to be, that derivative is 2, so we're going to have times 2 over, and then if you square out the 2x, that'll be 2x times 2x is 4x a second, like that. And then you can just put it together. You could write the answer that way if you want to. I'm just going to write it as negative 2 sine of inverse sine of 2x all over square root of 1 minus 4x squared, like that. That's as far as I'm going to take that. Okay? All right, chain rule. Okay? Now see, when you get back from spring break and do that second test and you do the gateway test, you know, it's all derivatives. It's unsimplified derivatives, but it's knowing your derivative rules. And anything can show up on there, including inverse trig functions. Generally, it's either inverse sine, cosine, or tangent is what we look at. Okay? All right, you guys got any questions about how I did that derivative? Okay? All right, let's go to this next one and see if we get this okay. All right, so what we have on this one is we have what kind of rule would apply on this? That's a product rule, right? So you got two functions. Your first function is x. Your second function is inverse sine. So you have to use the product rule. All right, so when we do this, let's go ahead and get it set up in the product rule. So you'll have the first multiplied by the derivative of the second, which is an inverse sine, like we know. Then backwards, you do the second, and then times the derivative of the first. Okay, so there won't be too much we do on this. There might be a little simplification. So it goes like this. The x comes down. The derivative of the inverse sine, that's the rule we just learned, is 1 over square root of 1 minus x squared. That's not a chain rule because that's just a basic rule. Okay. Then over here you would have inverse sine of x. And let's see, you got to do the derivative of the first. I forgot to put the x there, so that's 1. And then you have it. So I wouldn't do much with this one. I would just write it as x over square root of 1 minus x squared plus the inverse sine of x, like that. And that would be your derivative. That's as far as you can take it. The other thing you could do is you could get a common denominator and do that if you want to. Okay, so that kind of takes you through the basic idea of this derivative rule and how you're going to work out derivatives for inverse sine. Is there any questions on that? Okay, now we're going to move on. We're going to look at two more mainly, and then I'm going to give you the derivative rules for the other three. So I'm going to look at inverse cosine and kind of develop this idea. We're going to do a derivation of this one also. So the way this works is in a trig class, generally what you learn, you don't need to put this graph down, I just want you to pay attention to it for reference, is you have 1 there, you have -1 there, the cosine starts high, and then it cycles through these 5 key points like this. So again, what our goal is we're doing an inverse of that. When you do an inverse, you have to have a 1-to-1 function. Why is that not 1-to-1? Because it fails the horizontal line test, right? So what you would have learned in a trig class, hopefully, is what you do is you just ignore that part right there and focus on that. Then it's 1 to 1, right? So what we do is we only look from 0 to pi, and that gives us what the arc cosine of the inverse cosine looks like. So one thing you want to remember is on an inverse cosine, the domain is negative 1 to 1. Right? It includes those. Don't confuse that with the derivative that we're going to get to in a minute. And then the range goes from 0 to pi. Okay, so this is what the graph of an inverse cosine looks like. You're going from negative 1 to 1 and 0 to pi. Okay, if you tilt your head, it looks like a cosine, doesn't it? That's all that is this graph right here has been rotated and flipped. That's what happens when you take that graph right there, change it to that, you rotate it and flip it. Okay, and then it makes it. Okay, all right, so we have that. Now let's kind of look at this next thing here is let's do this. I want you to go ahead and draw a blank graph on this, and I want you to try to draw what you think the derivative would look like. Okay, so let's just kind of set this up and let's graph the derivative of we're going to do f prime of x on this. So we're going to go from negative 1 to 1, like that, and then we'll kind of see what we have. It's very similar to the inverse cosine, or inverse sine that we just did. So let's kind of think about what we have going on here. What kind of derivative do I have, negative or positive? Negative, and real negative, real steep. What's happening? It's actually getting bigger, right? That's a very small negative slope. That slope right there may be negative 100. But then you're getting into probably a slope of 1, right? Negative 1, actually. And then what happens is it just gets steeper. So does it make sense to you guys that slope of my tangent line is always negative? Okay? And when you're at 0, that's probably around a 45-degree angle, so that's around 1. Okay? So your graph would kind of do something like this. What you would have is this is a real small negative number because that's almost infinitely steep, so that would be way down there. This slope right here is negative 1, so you'd have a point like that. Okay, then what happens is it just gets steeper again, so it's going to do something kind of like this. So your graph will have this sort of a structure kind of like that. Does that make sense? Now, what's the difference between that graph and the graph of the inverse sine? They're flipped, okay? Negative. So you could predict that the derivative of the inverse cosine is just the opposite of what the derivative of the sine is, right? Okay? We're going to find out if that's all it is, okay? So that's what it looks like it might be. Okay, so what we want to do is we want to go ahead and do this implicit differentiation the same way. We're going to go ahead and develop this formula. And if you didn't follow the first time I did this, maybe you'll follow this now. It's very similar. So we're going to do the derivative of both sides of this equation. I'm just changing the inverse cosine to x equals cosine y. That's what it means. Okay? So let's do this implicitly, and let's see what pops out of this then. The methodology is the same. Okay? So what's the derivative of x? 1. What's the derivative of cosine of y? Negative sine y, then what? dy over dx. You're doing it implicitly, okay? There's a negative there now. So we have negative sine y times dy over dx, okay? Your job is to solve for dy over dx. So that means we're going to divide both sides by negative sine y. Okay, like that. Okay, I'm going to go ahead and write this just as negative 1 over sine y, like that, is equal to dy over dx. Okay, then we apply this trick, okay? So what you do is, because you can't really do much with a sine, but you can do a lot with a sine squared because there's an identity. What you do is you rewrite this as negative 1 over the square root of sine squared y, right? That's the same thing. I'm not changing the problem by doing that. Okay, now what you're going to do is you're going to pull out this identity that you learned in trig. You don't have to write this down. I mean, you can do this in your head. So what is the sine squared of y anyway? It's just 1 minus cosine squared y, right? So what I'm going to do is I'm going to rearrange this, and I'm now going to write this as dy over dx is negative 1 over square root of 1 minus cosine squared y. Okay, everybody following that okay? Okay, basic identities, okay. Now, the last part is this. You know what the cosine is, it's right here, okay? So what happens is, if you take this statement, which is what we were differentiating anyway, and square both sides, that just means cosine squared y is now becomes an x. Because you want your variable to have x in it, so that your derivative formula for an inverse cosine is going to be this, negative 1 over square root of 1 minus x squared. So it is the opposite. Okay, that's the way it worked out. Okay, now this is what you kind of expect because you already know this. You know a derivative of a sine is a cosine, but then if you do the derivative of a cosine, you get a negative sine. So it's the same thing. Okay, one of them's positive, the other one's negative. So it works exactly the same way. That'll help you remember that, hopefully. Okay, all right? So does that make sense, what I did there fairly well? Okay. All right, so what we're going to do with this is your general formula for a derivative of an inverse cosine. Again, negative 1 and 1 are not included because you end up having these vertical asymptotes. I don't remember if I had, do I have this little diagram on your handout? I guess I do. So those are vertical asymptotes, like that, okay? So if you know that rule, then working the derivatives out's almost the same as it is for an inverse sine, okay? All right, so let's go to the next page. We're going to do a little bit of work with derivatives, then we'll work with the tangent a little bit, and then the other ones, okay? Okay, so this one goes like this. Okay, when you do the rule for the inverse cosine, I've written all the rules down here. I usually only derive like the inverse sine and cosine. So here's the rule we're going to apply. Okay, this is a chain rule. So it goes like this. We're going to have, you have a negative answer now. Then you have 1 over the square root of 1 minus, and what are you squaring in this problem? 2x plus 1. Okay, so you're using a chain rule. Okay, like that. Okay, then what else you got to do? Since it's a chain rule, you multiply by the derivative of what's inside. Okay, once you start practicing and crunching these things out, you get catch on. It's just following the rule and doing the chain rule. So this is going to be negative 1 over square root of 1 minus 2x plus 1 squared. Now you could leave that alone if you want to. I don't care if you leave that alone. I'm going to go ahead and just square it because I do think that there's probably going to be some simplification. So I'm going to square this out in my head. The 2x times 2x is 4x to the second. Then remember you do the shortcut, you do 2x times 1 is 2x. Then you double that to get a 4x. Okay, if you don't like the shortcut, write it out twice and foil it on scratch paper. But you want to do that in your head. And then 1 squared is 1, so that'll give that. Okay, like that. All right? Okay, then what we have is the derivative of 2x plus 1 is 2. So that's an unsimplified derivative right there. Okay, is that clear? Okay. Now, let's see what we can do as far as simplification. We have negative 2. And what I'm going to have on this now is, I'm going to just kind of show you at the side of the paper here. You know, you would distribute the negative through there, like that. Then the 1's would cancel. So that would be negative 4x to the second minus 4x like that. So we got that. Now, there's a little bit more you can do on this. What do you think? I see one other thing I can do. Yeah, you got a factor. You can take a common factor out of the bottom, right? Okay. And because it's a 4, it'll come out of the radical, right? Because square root of 4 is 2. So what I'm going to do on this is, and you can take either a 4x out or just a 4. It doesn't matter. It's your call. It won't make any difference. Let's go ahead and just take the 4x out of that. Now I'm going to take a positive out, because I'm going to take that out of the radical. So that's going to leave me with negative x there. And then that's going to be plus or minus 1 there. Oops. Probably, but let's take a negative out. I'd rather do it that way now that I think of it. It doesn't really matter. But let's take the negative out. Then we'll take the square root of 4 out. Okay, doing it that way. That's different ways to do this. So that's going to be a x there. and a plus 1 there. You can multiply that out in your mind and verify that we've done that right. So we have that. Okay. So what I'm going to have now is negative 2. Now I'm going to write this like this. I'm going to put the 4 to itself, and then I'm going to write that just as negative x times x plus 1 like that. Okay? Now you didn't have to factor negative 4 out. You didn't even have to factor x out. It doesn't matter. The key thing is you want to factor the 4 out because that comes out of the radical. Okay, everybody with me on that? Okay, so that will come out of the radical, and now what you'll have is negative 2, square root of 4 is 2, and then you're left with this. And I'd probably just multiply that back together. Okay, you can leave it factored, or you could just do it like this. That's going to be negative x squared minus x. Those will now cancel out. So you're left with negative 1, and then you got it. That's good enough. Square root of negative x squared minus x. Now that one does need to be simplified down to that point. So then that would be where I would stop right there, write the answer. Okay, that one's got a lot of algebraic simplification in it. And again, the details of that, we're squaring out the 2x plus 1 and then working out the algebra to get that 4 out of the radical. Does that make sense what I did, algebraically speaking? Okay. All right, let's run through this example 2 and see if we can put this together now. Okay, now the big function in here, when you look at doing this derivative, what's the big function? Something to the third, exactly. How do you do a derivative of something to the third? Bring the 3 down, subtract the exponent, multiply by the derivative of what's inside. That's a chain rule, so you got to look at the big picture on this. Okay, so when we do this, we're going to have f prime of x is equal to 3 inverse cosine of x to the second times the derivative of the inverse cosine of x like that. Okay, that's just kind of like a power rule. That's a chain rule, so you got to multiply by the derivative of what's inside. Okay, so what you'll have is 3 inverse cosine of x to the second. By the way, there isn't any other way to write that. You can't write cosine negative 2 of x. I see students do that all the time. That's not right. That is an inverse. That negative 1 is an inverse. It's not a negative 1 power. So you got to pay attention to little things like that. So that's done. You can't do anything different with that. But then we know this rule. That's what we just learned. So that goes negative 1 over the square root of 1 minus x squared. And that's really it. If you put that together, you would just probably write it as negative 3 inverse cosine of x to the second all over square root of 1 minus x squared like that. So that's it. That's your answer. Okay? And that is just kind of a general power rule. And be sure you leave that inverse cosine x squared like that. That's all you can do with that. Okay? All right, any questions with that? Does that look reasonably decent? Okay, all right, okay. So see, now we're kind of in the chain rule. We're just doing it over and over again now. All right, so the next thing I want to show you is, let me kind of tell you what I expect you to know. Generally, what I have students memorize is 4 of these. I don't worry about the inverse secant and cosecant too much because they don't show up that much. So you want to be sure that you know the inverse sine, inverse cosine, inverse tangent, and inverse cotangent. Those are actually pretty easy to remember. The secant and cosecant doesn't show up very often, but the inverse tangent shows up a ton in calculus too, over and over and over again, just for a certain type of thing that we work with. So the thing that you can kind of remember on this too is, remember I said if you do a derivative and it begins with c, what happens? You have a negative. Same thing happens here. Okay, so that'll help you a little bit there. And then it's just cofunctions. See, the more patterns you see, the better off you're going to be with memorizing. A sine and a cosine are cofunctions. So the only difference in the answer is the minus. Tangent and cotangent are cofunctions. The only difference is the minus. Same thing with secant and cosecant. That's the idea. Okay, so that's how that works out. Okay, so these are the rules that you're going to encounter. It turns out on an inverse tangent that it's for all real numbers. X can be any real number. Okay, and that's because of how the graph works on an inverse tangent. Okay, so the inverse tangent is going to be 1 over x squared, like that. Okay, so then the inverse cotangent is just -1 over 1 plus x squared. So get those 4 memorized. Now we're going to go ahead and work a little bit with the derivatives of the other inverse trig functions next. So what I want to show you on this a little bit is this idea. Let's see, I want you to do something on your calculator before I do derivatives. I want to do one more thing with the inverse tangent. So let's do this, just kind of to remind us of something from trig. Put your calculator in radian mode. Press mode and then go to radian. And then we're going to do a graph of the inverse tangent, just kind of remind you of how that goes. That graph of the inverse tangent, I can think of times in Calc 2 where we have to remember what that graph looks like for certain reasons. So let's go like this. If you graph an inverse tangent, you're going to go secant tangent to get the inverse to come out, like that. And then I'll give you a viewing window to do on this. And then I want to kind of talk about the derivative on this a little bit too, I think. Okay, so next thing I want to do is, for the window, let's do something kind of like this. Let's go like -10 to 10 on x, not like that, of course, -10 and then like this. Okay, probably scale by 1. And then for the x minimum, what I want to have you do on that is go from -pi over 2, like that. And that's going to just change that to decimals, like that, -pi over 2, and then go to pi over 2, like that. Okay? All right, now I'll slide that over here so you can refer to that if you need to. So that's the window. And then go ahead and do the graph. And this will be what the graph of the inverse tangent looks like. So if you look at this, you probably remember the graph of the tangent did this, right? Everybody remember that? Same kind of thing. It's flipped, it's rotated and flipped is what it is. So what happens is, you may remember that when you graph a tangent, it has vertical asymptotes at -pi over 2 and pi over 2. Well, what happens to the vertical asymptotes? They turn into horizontal asymptotes, okay, because you're doing an inverse. So you actually have a horizontal asymptote at pi over 2 and -pi over 2. And the graph goes on forever. So that's the reason why the domain of the inverse tangent's all real numbers. The range is -pi over 2 to pi over 2. So that's how that basically works out. Okay, now if you were going to look at a derivative on this, okay, just basic idea, if you were going to graph a derivative, this is kind of what happens. That derivative is close to 0, right? Okay, the derivative though is getting bigger. And then when it gets there, it's real steep, that's a pretty big value. And then what happens? The derivative gets smaller. Everybody with me on that? Starts from 0. I'm going to try to trace it as I go. 0, a little bigger. It's a high point. Then it starts kind of going back down again to 0. So the graph of the derivative is going to almost look like a bell-shaped curve, kind of, in a way. Okay, and if you graph out that 1 over 1 plus x squared, you'll have that. So I also want you to put in the derivative. The derivative is 1 over, we're not going to derive this, but it's 1 over 1 plus x to the second. Okay, like that. Graph that out and see if you don't get a bell-shaped curve coming out of that too. 1 over 1 plus x to the second. Okay? So it should now graph out the derivative. Kind of starts at 0, hits a high point, does something like that. So that's it. All right? So that's also kind of a nice thing to know, is how these things relate to one another. Okay, so let's do some derivatives then. And I'm going to refer to this. I don't know if this is on your handout in a different page, but those are your derivatives right there. So we're just going to refer to these as we go through these then. Okay, so to begin with this one, if we do a derivative of an inverse tangent, you're applying that formula right there. Okay, so let's do this. This is a chain rule. So you have f prime of x, you're going to say 1 over 1 plus something squared. What's the something? e to the 4x, right? This is a chain rule. It's not just applying the definition, it's applying the definition and the chain rule. So what you're going to have there is e to the 4x. Then what else do you got to do? Times derivative of the function inside. That's it. Okay, that's how you set that up. Okay, so if we do this now, we're going to have 1 over 1 plus. Now what is e to the 4x squared? What is that? Good, e to the 8x. I asked that question because most of the time I see students do 4x squared. Now you're multiplying exponents. 4x times 2 is 8x. So that's e to the 8x, like that. Okay, now this derivative, we got this down, hopefully that's itself, times derivative of exponent is 4. Okay, so that's your derivative. If we put this together, I would just multiply straight across and get 4e to the 4x over 1 plus e to the 8x, like that. That would be your simplified derivative. That's all you can do. You can't cancel, no factoring, you're done. Okay, everybody follow that okay? So that is a basic chain rule for an inverse tangent. That's how you're going to apply that, okay? All right, now the next one is a cosecant. So the cosecant, you want to follow this formula. You just do exactly what the formula tells you to do. You don't have to, I don't require students to memorize the arcsecant and arccosecant's derivative, but I do require you to memorize the rest because they're more applicable. Okay, so when we do this, and we do our derivative, we're just going to do exactly what the rule tells us to do. The function we have embedded inside is a tangent of e to the x. So we have a function and a function and a function. Okay, actually is what we have. So it'll go like this. We'll say negative 1 over the absolute value, and don't put an x there, put whatever that argument is. So what's going to go in there is a tangent of e to the x. Okay, like that. Okay, so that's going to go in the absolute value, and then you'll have the square root, and it goes backwards, so you'll have that function squared minus 1. So again, put that argument in there, tangent e to the x like that, and then since it's a chain rule, you're also going to have to multiply by the derivative of the tangent of e to the x. So that's how that thing gets put in the formula, and then we got to do that derivative and then just simplify it up. So again, it's negative 1 over the absolute value of the argument squared minus 1. Does that make sense? I don't just put an x there, put that function tangent of e to the x in there. So when you do that, you would have negative 1, you're just going to leave that absolute value alone. Okay, like that. Okay, then what we'll have here is, same thing here, I'm just going to leave that the way it is. You could write this if you wanted to as tangent squared of e to the x, because that's what's being squared is the tangent. The e to the x is not being squared, so you have that. Okay, then what we'd have from here is now we got to do the derivative of a tangent. So what's the rule for a derivative of a tangent? Secant squared, right? The derivative of a tangent is secant squared. Okay, we have a chain rule in this now. So when you do that, that goes to a secant squared. So that will be secant squared of e to the x. But by chain rule, you also have to multiply by the derivative of e to the x. Okay? And you can do that in your head if you want to, but just to emphasize, that's what you're doing, a chain rule and a chain rule. Okay, so now you'll have, when I put this all together, that derivative right there goes to e to the x. So if I put this in a numerator, I'll have negative e to the x, secant squared of e to the x, like that, all over the absolute value of the tangent of e to the x. And then we'll just write that as square root of tangent squared e to the x minus 1. Okay? And that's as far as I'll take that. And then that should be good enough for our answer, like that. Okay? Okay? These don't show up as much, but if you follow the rule as you're doing your homework, you should be fine as long as you can do the chain rule okay. All right? Okay, you guys see what's going on there okay? Okay, I'm going to give you guys about 5 minutes to work these out. I'll put the rules here. These are just tangent and cotangent. I do expect you to know how to memorize the tangent and cotangent formula, because you're going to use these quite a bit, particularly inverse tangent. That's very useful. And the only difference is the arc cotangent has the negative. So go ahead and do these. These are chain rule problems. And simplify as far as possible. Then I think we'll probably go through one application here to finish this up. I don't think these should be very difficult because they don't have a lot of simplification going on in it. Okay, so I'm going to go ahead and set this first one up here. Okay, so when we do the derivative, f prime of y, okay, what you should do is you just do 1 over 1 plus, and then you do that argument. It's going to get squared. So you're going to have 2y the second minus 4 squared. And then you should have multiplied by the derivative with respect to y of what's inside like that, which you can do that in your head. And I think with this one, there isn't going to be any simplifying. So what I would want you to probably do on this, you're okay to leave that alone if you want to. I'm going to go ahead and square this and do that. So the first term, if you do 2y squared times 2y squared, that's going to be 4y to the fourth. Okay, when you do that middle term, that's negative 8y to the second, but then you double it to make it negative 16y to the second. And then if you square the negative 4, you're going to get a plus 16. Okay, like that. And then when I do this, that derivative is going to be just 4y like that. Okay, now if you left that alone and didn't square it, it doesn't really make that much difference on this problem because I don't think you're going to have any simplification anyway. So I'm just going to write the answer as 4y. And then combine the like terms, I'm going to have 4y to the fourth minus 16y to the second, and then 16 plus 1 is 17, like that. Okay, well, that's it. That's what you do. Chain rule. Does that look okay? Okay, second one is real simple as well. That was supposed to say f of x. Okay, so I'm really looking at this. I don't want to mix the variables up. Okay, so if I do this, what I'm going to have on the formula for a cotangent, it's the same as the arctangent, except it's negative. So it would be negative 1 over 1 plus the argument, which is e to the x squared, times the derivative of what's inside. So that's how you set that one up with a chain rule. Okay? All right, so let's see what we've got down here. I see students mess up on this all the time. What's that? E to the 2x. Multiply the exponents. Not e to the x squared. I see that constantly. So this is negative 1 over 1 plus e to the 2x. The derivative of e to the x is itself. When you just put it in one fraction, you would have negative e to the x over 1 plus e to the 2x, and you can't simplify that any further. That's as far as you're going to take that. Okay? Both of those problems were done essentially the same way, using the chain rule and following the general formula for the derivative. Okay, so let's do, I think one more thing is what I want to do. I want to do a tangent line And then we got that last application problem here. So let's do this tangent line. And so this one, what we're doing is just doing something with an inverse cosine. So let's work with this. Again, if I want you to find an equation of a tangent line, you're always working with that formula that you're familiar with. And when you find m, what are you doing when you find m? You're doing a derivative, right? That's where the calculus comes into play. Basically, in this problem, y is going to be pi over 3. That's given in the point I gave you. And then x1 is going to be 1 over square root of 2. So you've got that. The big job of the problem is just figuring out what m is. So we need to do a derivative, and this time we're doing a derivative of an inverse cosine. Okay, so let's go ahead and work with the derivative then. Okay, if you want to look at the formula now until you get that memorized, there's your formula right there. So we're going to apply that with a chain rule. So that's going to be negative 1 over the square root of 1 minus something squared times the derivative of that something. Okay, and that something is x squared. So that's how that one gets set up, as like that. Okay. All right, now we need to finish that up. We're going to have to evaluate that to get a numeric value of that. So the derivative of x squared is 2x. So that's going to be negative 2x. Then we've got the square root of 1 minus, and then x squared is x to the fourth, like that. So that's what f prime of x is. Okay? Everybody getting that down? Okay. All right. Chain rule. All right. Now let's go to f prime of 1 over square root of 2. Now it might make sense on this to go ahead and just put that in a rationalized form. So that's square root of 2 over 2. That's what I'm going to do, is just plug in square root of 2 over 2, because I'm probably going to have to do that someplace in the problem anyway. And we're going to simplify that out as far as we can. Okay, you know that from trig. So we have negative 2. Now you're just going to replace all of the x's you see with root 2 over 2, and then we're just going to see how simple we can make this. So that's square root of 2 over 2 there. And then we've got square root of 1 minus square root of 2 over 2 squared. So hopefully that's not going to be too bad. Okay, so the numerator, the 2's cross out, leaving just a negative square root of 2. So we have that. Okay. And then in the denominator, what I'm going to have is the square root of 1 minus. And if you square this thing out, what do you get? Yeah, what did I do? Oh, it's to the fourth. Okay. All right. I could tell some people looking at me funny. Okay. Let's try again. Okay. Well, let's do it this way. If we do this to the fourth power now, let me just sort of write this at the side. If you're doing the square root of 2 over 2 to the fourth power, you can think of this as the square root of 2 to the fourth under the radical over 2 to the fourth. Well, that's really 2 to the fourth is 16. So you get this. So that looks like that would be 4 over 16. So that would reduce down to 1/4. Okay, so that's what that is. Okay, that's one way to look at how to do that radical. So I'm just going to write that as 1/4. Okay, well, you want to get a common denominator probably on the bottom. So you would have negative root 2. Okay, this is I'm going to write that as 4 over 4 minus 1/4, getting a common denominator. So that's negative square root of 2 over, and see, this is now the square root of 3/4. And then you can take the square root of 4 to get that. So if you do that, let me move this thing over the side here. So if you do that, you're going to have negative square root of 2 all over the square root of 3 over 2, right? Okay, now that's a division problem, so you want to go ahead and divide that fraction. So that's going to be negative root 2 over 1 times the reciprocal, like that. So that should give us negative 2 square root of 2 over square root of 3, which you could rationalize if you want to. Okay, so that's what the slope is. I don't know if it makes that much difference to rationalize that now or later, so I'm going to go ahead and just leave it in that form. Okay, then what we're going to do is we're going to pull out our point slope formula and put it all together. Now that's a lot of arithmetic. Was that hard? Because these are the issues people get into in Calc 1. You got to handle arithmetic when it shows up, just doing fundamental things that you've done in the past. Okay, so what we're going to do to put this together now is we have y minus pi over 3. Okay, that's your y value. Equals the slope. Let's just leave it in this form. Or you can rationalize it if you want to. It doesn't really matter. Then we're going to have x minus. Now I'm going to go ahead, when I put 1 over square root of 2 there, you can leave it the way it is or you can rationalize it. I'm just going to leave it the way it is because I see some sort of cancellation. Okay? The hardest part of the problem to me so far is all that arithmetic. What do you think? Okay, now just multiply it out, solve for y, and we'll see what we have. So we have y minus pi over 3. Do a distributive property. That's going to be negative 2 root 2 over root 3. Okay, multiply that out. You got a negative times a negative is a positive. Notice that the root 2's cross out. Okay, so then that would leave you plus 2. And there should be an x there, left off the x. So that would be 2 over root 3 like that. Now, we're not going to do much with this problem. I mean, it doesn't matter if you leave things unrationalized that much to me. So we're just going to add pi over 3 to both sides, or just move that. So what you would get is y equals negative 2 root 2 over root 3x, okay, plus 2 over root 3 plus pi over 3. Now, you can rationalize if you want to on that. It's probably a reasonable thing to do, so I'm going to go ahead and do that, and then that'll give me the answer that I am looking for on here. Now, see, these are unlike terms. You can't add the pi over 3 to 2 over root 3, so you just leave that alone. So what I'm going to do is work with this. I'm going to go ahead and rationalize this. I probably should have done that earlier in the problem. So I'm going to do that, okay. Well, okay, that is negative 2 root 6 over 3 is what that's going to become. Okay, and then when you got 2 over root 3, any of this stuff, if you can do it in your head, do it in your head. That's 2 root 3 over 3. So I'm going to write my final answer as y equals negative 2 root 6 over 3x plus, then the 2 over root 3 is 2 root 3 over 3 plus pi over 3 like that. Okay, that's the equation of my tangent line right there. Bunch of arithmetic on that, but beyond that, it's not that complicated. Okay, so that's what I'm going to end up getting is that answer then. Okay, okay, does everything look okay with that? Okay, now I'm going to go ahead and with this one, this next problem takes a little bit too much time, so I'm going to go ahead and just let you go. And we'll do this last example next time because it takes a while to set that one up. Okay, go to Pi Day. Pi Day is getting ready to happen in 10 minutes. Okay, go there, just right down the hall.